Assalamualaikum. Welcome to the new lecture on practicals. The practicals for today is about running logistic regressions for data with ordinal outcome. We have 4 tutorials for running logistic regression for data with ordinal outcome. Let's first go to tutorial number 1, where we'll talk about introduction to cumulative link models, or also known as proportional odds model. Let's enlarge this one first. In the first tutorial, we will use Ordinal package by Rune Hubo B. Christensen, and the tutorial can be found here. Cumulative link models, or CLSM, are powerful models class for this kind of data, the ordinal data. In addition to ordinal package, you have also the function POLR, POLR from MASS package. PGAM package also include CLM function to run cumulative link model, and in the RMS package you have LRM and ORM to run logistic regression model and ordinal regression model. So what we will do in this practical is to run cumulative link model. This is also known as proportional odds model, and we will use ordinal package. First, to prepare for the analysis, we will use these packages: the ordinal package, tidyverse package, and broom package. So to load the packages, type library ordinal, library tidyverse. So ordinal package contains the function that we'll be using to estimate the model for cumulative link logics. Tidyverse, the package useful for us to do data wrangling and data plotting or data visualization. We'll also load library Heaven. Heaven is a package to read statistical data. And Broom, we will load Broom 2 by typing library Broom, because Broom can produce results in a data frame. So let's read a data. A data set that we'll be using is wine from ordinal package. We will convert the file to an object of table and name it as data.o. We will examine data and we will summarize the data. The function read_dta comes from Heaven package. Then you specify the dataset. The read_dta will read stated data, and we will store this data as an object called dat.o. Use glimpse to return the names of variables and the number of observations. So we have 72 observations, 72 rows and 6 columns. We see that the response variable is coded as a continuous double variable, and rating, temperature, contact, bottle, and judge are also coded as double variables, but with label. It means that these variables are coded with number, but that those numbers represent some kind of a categories. So we use a function summary to return the results of the statistics, the mean, median, and some other results, and of course this will return the statistics of numerical variables, even though you know that some of these variables are not actually numerical variables. They are categorical variables but coded with numbers. The outcome variable is rating, which has values starting from 1 until 5. 1, 2, 3, 4, 5. What we are going to do next is to convert rating, which is now a numerical variable, to a categorical variable. We know that from here, this is a numerical variable, but the number represents some categories. So what we do here is we read this data, then we use percent bigger than percent, is known as pipe, P-I-P-E. What it means here that from this data we do this, okay? From this we do this. So here from this data we run this function mutate, this label as factor. What it means is from this data set we create new variable. If the variable is a categorical variable, it will be converted to a categorical variable, okay? If it contains label, then they will be converted as factor or categorical variable. So by doing this, you don't have to do, or you don't have to convert each variable, okay? If not, you have to do this many times. By running this, by running mutate if, all the variables that are in the label class will be converted to a categorical variable. So when you see here, with only one function, all the variables that are double with label have been converted to categorical factor variable. To estimate, we will run the proportional odds model, or also known as the cumulative link model. The function in Ordinal package is CLM. So let's run the first model, a simple model, which is the probability of outcome yi equal or less than j. which equal to theta j minus beta 1 temperature minus beta 2 contact. So be careful with this notation. They are negative. So let us run the first model, and let's name the model as O1. CLM, the outcome variable, is rating. The predictors are temperature and contact. Data is dat.o. Run it and type summary of the model. It will return the log odds from the estimate. So this is the variable temperature, and this is the variable contact. This is warm, so the reference will be cold. The contact, yes, so the reference is no contact. So this is the threshold coefficients. Most of the time the threshold coefficients are not that useful for us. You can type tidy O1. This is a function that comes from Broom package that will convert the results of a model into a data frame. So it will return the estimate, the standard error, the statistics, p-value, and type. If you run this in Stata, the function will be ologit, the outcome variable, and the predictors. So you have the coefficient, which is the log odds 2.50, 1.52, 2.50, 1.52, but be careful, the threshold coefficient will be different because Stata use cut while CLM use coefficients. So variable temperature and contact are positive. So it means that at the warm temperature associated with higher categories of outcome, the presence of contact associated with higher categories of outcome. Remember, the outcome variable is coded from 1 to 5. So what we are looking at is where we interpret this, the higher the value here, the higher will be the categories of the outcome. So for example here, the odds ratio of bitterness being rated in category J or above. Category J or above is equals exponential of beta 2 yes minus no, which is 4.61. This will be for, I think, for this one, right? Let us check after this. So again, come back to the tidy function here. You realize that there is no confidence intervals here. So to reduce the 95% confidence intervals values, what you can do is to add another argument conf.int equal true. This will produce the confidence interval, the lower CI and the upper CI at 95% level. And if you convert this to odds ratio, then add another argument exponentiate equal true, conf.int equal true. So now what you have here are the odds ratio: 4.61, 12.2 is 4.61. So what this tells you is this: at warm temperature, the odds of bitterness being rated in category J or above is 12.2 higher than at cold temperature when adjusted for contact. When controlled for temperature, the contact in the yes category has 4.6 times higher odds of bitterness being rated in category J or above than the contact in the no category. Now let's go to inferences. Though we partly did that just now by looking at the confidence intervals, there are two other things that we can do. One is to look at the p-values of each of the coefficient, and number two is to do model comparison when we talk about making inferences. So again, we perform inferences by checking the word-based p-values, calculating the confidence intervals, and do model comparison, perhaps by using the likelihood ratio test. What you can do is to run this. Okay, for example, let's say we have a variable temperature as a predictor, and we name this model as O1b. We can compare this O1b with previous model of O1 using the function ANOVA and specify the argument test by setting the parameter of chi-square. So this will compare the two models, the O1 and O1b. It will return the difference of the AIC between the two models and the p-value to indicate how big the difference between the two models. If the p-value is less than 0.05, then if you take the level of significance at 5%, then it shows that the two models are different. To make a prediction, you can predict the probabilities. You can predict the probabilities that the ith observation falls in what category. Okay. For example, let's make to run this. Let us make a new data. So from this data, the OTAT.O, I select all columns except for the outcome variable. Okay, I select everything except for the outcome variable rating. That's why it is minus here. And I call this data as new.data. Then next I use the function predict. Predict what? Predict this model O1 using this new data. So and I want to store this result as prob.01. And then I examine the first 6 observations and the last 6 observations by using the function head and the function tail. This will return the probability of the first observation stays in category 1, category 2, category 3, category 4, category 5. It means that based on this model, if we know the value of the temperature, and if we know the value of the contact, we can predict the probability of each observation stays in what category. For example, the first observation, there is 20.7% probability to be in rating 1, 57.1% in rating 2, 19.2% in rating 3, 2.4% in rating 4, or 0.7% to be rated in category 5. Okay, let me rephrase this. For observation number 1, the probability of being rated as category 1 is 20.7%. The probability of being rated as category 2 is 57.1%. The probability of being rated as category 3 is 19.2%. The probability of being rated in category 4 is 2.4%, and the probability of being rated in category 5 is 0.7%. You sum all this number, you'll get 100% or 1. If you want to predict what is the most likely class each observation will fall, then you can use the function predict. The model, in this case, the model is model O1 argument type equal class. So when and then I use this head to see the first 6 observation, head of class.O1, it will return the most likely class each of the observation will fall. For example, observation number 1, the most likely rating that observation number 1 will get is 2. Observation number 2, the most likely rating is 2. Observation number 3, the most likely rating is 3, so on and so forth. So if you look here, the highest probability is for observation number 1 is rating 2. For observation number 2, also rating 2. For observation number 3, rating 3. Is compatible with these two. This is another way of making prediction by using expand.grid to make a new data set. So you can try this. Okay, for example, if I have this data set, temperature cold, contact no, temperature warm, contact no, temperature cold, contact yes, temperature warm, contact yes, and I want to predict the linear predictor and I want to predict the probability. These are the functions. Predict what model, which data, and what type. So you get the linear predictor's value for each observations, and this is the probability for this data. So there are 4 observations, 4 possible combinations here. That's the reason why you end up with 4 rows. You can, use the function cbind to combine this and this, right? One assumption that you have to check when you run proportional odds model is the proportional odds assumption. So there is a function nominal underscore test in ordinal package that can run this. So what you do is just type nominal underscore test and the model, and it will return the results of the test. So if you set the p-value of 5%, if the values of probability here is bigger than 0.05, then you can say that they have met the assumptions of proportionality. The other option is to run CLM and to specify that the nominal variable for this one is tilde contact. So you can compare this nominal with the O1 model and to see if there is huge difference, if the p-value here is less than 0.05. If the p-value is less than 0.05, then it tells you the proportional or assumption is violated. So you want to see the p-value here bigger than the level of significance. Again, when we come back to prediction, you can predict the probability. You can use the ordinal package, or you can use polar package. For example, let's say we run polar, and polar function comes from a mass package, so you have to load the library mass first. So type library mass, use the function polar, the outcome variable here, the predictors here, the data set, and name the result as mpolar. Type summary that will return the results. Type predict the model, this model, and type equal probs. This will tell you the probability. So you can use polar or CLM functions. So polar in MASS package and CLM from ordinal package. So to calculate the prediction manually, you can refer to a discussion on stacks exchange here. And this is the formula to calculate the probability of the y value equal or less than g. So for example, in this example, we run the prediction, and we predict the linear predictor, and we get the coefficients for this model O1, and then we put this inside the equation. You remember in this equation, the exponent should be 0 minus beta 1 x1 divided by 1 plus exponentiation beta 0 minus beta 1 x1 plus so on and so forth. So the logic, so you have 5 categories, right? So five categories. The rating starts from 1 and at 5. So if you can calculate for 4, then the other one it's quite easy to calculate. So logic 1 for coefficient 1, logic 2 for coefficient 2, logic 3 for coefficient 3, logic 4 for coefficient 4. Okay. So this is for this one, right? For the threshold. So when you type this, you'll get back these values, the threshold values. So the probabilities are calculated like this. Probability of less or equal 1 equals 1 divided by 1 plus exponentiations of minus logit 1. Probability of y less or equal to equals 1 divided by 1 plus exponentiations of minus logit 2. Probability of outcome 3 or less equals 1 divided by 1 plus exponentiations of minus logit 3, and probability of y is less or equal 4 equals 1 divided by 1 plus exponentiations of minus logit 4. So so if I use C bind here, then I can see the probability here, right? For this is for the first observation, okay, the first observation. So this equals with this one 0.206, 0.57. So this is manual calculation, right? So this is by asking R to run for us, okay? So this is a way of of making sure that you understand how to calculate the probability. So just put the value here, right? So just put the value here. For example, for this is for, right, so I think this is for observation number 4th observation. Okay, this is for the 4th observation, where you have warm and yes. Okay, warm and yes, 1 and 1. Where is it? Okay, so you put 1 and 1 here. Okay, 1 and 1. So I name this as lp.o1.bx4, and then calculate this for each of the threshold. Okay, and then you get the value here. So when you put it nicely in a vector, then this is the probability that you'll get, which is the same as this one, right? This is our manual calculation, and this is the computer calculation, the values are the same. So in tutorial 2, the materials come from Applied Logistic Regression book by Hosmer and Lemeshow. I highly recommend the book. In the book, it describes 3 models: the adjacent category, the continuation ratio model, and the proportional odds model. Of course, what we discussed just now is this one, and many papers, when they describe or when they analyze ordinal outcomes, they use proportional odds model. But there are other alternatives to run regression for ordinal outcome, that is by using continuation ratio models or adjacent category model. So because of the data set, I have to transform data to mesh what the book shows, right? So again, I load library tidyverse. If you have loaded this previously, you don't have to load this. So that the data set name is lowbwt.dta. I read this using the function read underscore dta, and I use the function summary to return the values or the brief statistics. I use the function glimpse to look at the number of observations and the class and names of the variables. Pay attention that these variables are double variables and these variables are double variables, but they are labeled. If you use the function stir, then you will see for the last 1, 2, 3, 4 variables, 1, 2, 3, 4, they are labeled. Okay, they are labeled, and these are their labels. So what I do here is to convert all label variables to a categorical variables by using the function mutate underscore if, and you will automatically convert all variables that are classified as is labeled to categorical variables. The function detach package mesh, if previously you have loaded this package, you have to detach because the function select in mesh and the function select in tidyverse conflict. So you have to detach first this one if you are using mesh package before. If you not, then that's fine. I'll create a categorical variable bwt4, and I use the function cut, and I cut variable weight using this cut of values, and I labels this. So when I group this and summarize the values, I get the minimum and the maximum. This is done just to make sure that what I have done here is correct. So then I need to reverse the order the outcome to reproduce the result in the book. So you don't have to do this if the data is already appropriate for your analysis. Okay, in this case I need to do this transform the variable and reverse the coding just to make sure they are compatible with the contents in the book. So I use the function factory level to change the level of the variables to this. Then create an ordered or ordinal variable. Okay, so there are two steps here to change the level and then to order it to make it into ordinal variable. For the adjacent category model, you can um, um, if you can, okay, if you go here, so what I want to show here is the adjacent category model. Okay, adjacent category model or multinomial or baseline logic model. I create a new variable bwt4b, which is uh, a variable bwt, but I relevel it. I change the ordering, the levels of the variables. Okay, so in this case, I run a function vglm from library vgam. We learned this before. Let's take only one predictor, smoke, and specify multinomial here and specify the data set. So this is to produce table 8.16. Okay, table 8.16. So I run this. I type this summary table 8.16. So I get the result that is similar to table 8.16 in Hosmer Lemeshow Applied Logistic Regression book. To get the relative risk ratio, I just exponentiate the value of the coefficients for this model. Okay, this is the model table 8.16. I get the coefficient, I exponentiate the coefficients. For continuation ratio model, I use GLM function, but this takes quite a number of steps because this is like doing a separate binary logistic regression. Okay, separate binary logistic regression. So I need to do GLM. Then I need to compare this pair first. Then I need to compare this one, and I need to compare this one, right? So to do that, because I run separate binary logistic regression, so I have to do lots of data filtering. Okay, but if your data is already good, properly ordered, you don't have to do this. Okay, I'm doing this because I want to replicate what's in the book. Okay, for example, in table 8.16, so on and so forth, right? Tutorial number 3 is again we run a cumulative link logic model. But this one is for this data set, right? For the LOWBWT, the low birth weight data set from Hosmer and Lemeshow. So the outcome is BWT4 and covariate is LWT. We use the function CLM from the package Ordinal. Let's start off simple with LWT as the predictor. Function CLM, data DAT03, and we name this model as O.1WT. You can put whatever name here. Type summary of the model to get the value of the coefficients and other parameters. Then you can use tidy to convert these results to a nicer data frame table. Specify the confidence interval true to get the lower and upper confidence intervals. Set the argument exponentiate true to get the relative risk ratio. Okay. So if you look at the value here, the value of LWT 0.0127. So this is the coefficient of the LWT, the logos. It shows that the heavier the LWT, the heavier, then the value of BWT also increases. Okay, the value of BWT also increases. Right. So the interpretation here is there's a few ways. There are two ways of interpreting proportional odds model. Okay, which is quite confusing. But you can go back to the book, to Hosmer-Lemscher book, and look at equation 8.25 on page 300 in the applied logistic regression book to learn how to interpret this. So if you change from 1 to 10 pound, right? 10 pound. For every 1 pound increase in LWT, the odds to get lighter baby reduce for about 2%. Okay. 1, 2. Okay, 1 for 2%. Let us check again. Okay, what does it say? Right, because when you exponentiate this one, exponentiate, this is 1 pound, and this is the coefficients for this one 0.0127, which will convert to 0.013. And why it is negative here, you have to go back up here to understand the equation. Okay, where is it? Okay, this one. Okay, this minus here, right? This minus here. So just now. Okay, so when you exponentiate this one, so you get the value of 0.98. So it means that for every 1 pound increase, the odds to get the lighter baby, because you know the in proportional odds model, you are looking at the lighter or the smaller category versus the bigger category. Okay, the smaller category versus the bigger category. Okay, so that's why you interpret as lighter. So so lighter baby is code as 1, and then the bigger the baby, the bigger the number. If the baby if the mom's weight increased by 10 pound, you get the value of 0.88. It means that if the mom's weight increased for 10 pound, the odds to get the lighter baby reduced for about 12%. 12%. So I think you should this one I think you should change to plus. Okay, because that's for this interpretation. Okay, this for this. Okay, and this should be positive. Okay, So, and then you can interpret the other way around. Okay, for 1 pound increase in mom's weight, the odds to get heavier baby increase for about 1.3%. Okay, 1.2%. But this one is minus. You can just remove this value because now you want to know what will be the odds to get heavier baby. So because the direction is now the other way around, so you have to change this from negative to positive. Okay. Similarly, if the weight increased for about 10 pounds, what would be the odds to get heavier baby? Change this to positive. This becomes 1.135. It means that for every 10-pound increase in mom's weight, odds to get heavier baby can increase for about 13.5%. Okay, 13.5%. So you can interpret two ways: lighter versus heavier, heavier versus lighter. Okay, just by changing the symbol here. By default, the symbol here is negative. Okay, so you're comparing the smaller category to the bigger category. So if you use a polar function in mass package, it's easy. Just use the function polar, specify has equal true, then you get the same results. Another way of checking the proportional odds assumption in polar is to use library brand. Okay, library brand. Sorry, to use a brand package. To use a brand package. Okay, you have to install this and then you have to load this using the function library and then the brand package. Then use the function brand and the model. Test if the parallel regression assumptions hold or not. But this can only be done if you run the proportional odds model from polar function in the mass package. You can't do this if the object here comes from CLM function. You can't. Okay, you have this only applicable to the model that is run on polar function. So in tutorial 4 there is another example that you can use. Okay, you can use so I show two ways of estimating the proportional odds model, one using the mass package, the function polar, and the ordinal package and the functions is CLM. So results is again similar: 0.021, 0.6, 0.067, 0.006, 0.006, 0.52, 0.52. Okay, and the threshold coefficients are also similar. But again, if you run this in Stata, you'll get the same estimates, but you get different cuts. Okay, because Stata use cuts, and then but ordinal and mass package use threshold coefficients. Okay, predict And then again, go back and I think tutorial 2 or tutorial 1, look at how we can do prediction. So predict probability, predict class, and predict the linear predictor. Okay. So this is when we use new data for prediction. Okay, we make a new data using data.frame, and the variable here, the value of the variable, and then predict what model, which data, and what kind of prediction you want to make. So this is the model here. This model, okay, and data that we want to predict is this new data, which actually the 1977 year of 1977, man, PRST equal 20, age 64, ED 16, and white. To get a probability of being in SD class, D class A, and SA class. Right. So there is 4.43 where you can replicate this data probability, which is optional for you to do, right? Optional for you to do. Lastly, about the software. Data, the way to estimate is just to run all logic and the outcome variable and the predictors, and then for prediction, run the predict function, what you want to predict, and p. This is the logic formula, this is the probability formula. So this is for SAS. Look here, this is the probability of y less or equal than g, and for SAS it used the probability of y equal or bigger than g. So R and Stata are especially for ordinal package and mass package use this logic formula, unlike SAS. Okay, so there's a bunch of references that you can go and read. And Hosmer and Lemeshow book is always is something that you have to read, and Clembound in his book Logistic, Regression, Self-Learning Text is also very, very important. And there is a short video to show how you can calculate the probability in YouTube. Right, thank you.